So what is GKR? Can you guys read this? It's too big, too small. It's fine. Okay, so the idea is, given a circuit C, we're going to, instead of having to compute the entire circuit C by yourself, you can delegate it to a prover who would do the computation for you and prove if the computation is correct in an interactive protocol. And the main idea of how you can do it, so let's say this is a depth D, and size S circuit. What you're going to do is you're going to take every single layer of the circuit, extend it to a low degree extension. So this is going to be V hat. So basically you take all the wire values on each layer, find a low degree extension of it, and then you're going to have some low degree extension of each layer. The output layer is going to be V0, then it's V1 on the second layer, and so on. The final layer is going to be VT. And the way GKR works is essentially as follows. You're going to reduce some claims about the top layer, the output layer, to claims about layers below it, and you're going to keep doing this until you reach the bottom layer, at which point the verifier can check themselves. So at the beginning, you might have that the output gate, you want this to be equal to 0. You're going to reduce this via the sum check protocol to 2 claims. So let's call these Z11 equals maybe the value V1, and also the claim that the low degree extension on a second point is also equal to a different value V12, and this is done via sum check protocol. And then you can do this again. So last time, I showed how to kind of do this in a 2-to-2 fashion. So we're going to reduce 2 claims to 2 claims in the next layer. I'm just going to keep going. At the end, you're going to reduce via sum check to the claim about the output layer. So maybe ZD1. Okay, and at this point in time, this is just a low degree extension of all the input gates, which is size n. The verifier knows what all these inputs are, so they can compute the low degree extension by themselves. And so altogether, this is going to take the prover time poly s to prove the computations done correctly to the verifier. And the verifier will run in time, let's see, it's going to be d times poly log s. Plus like n times main poly log s also. Okay, this is just what we did last time, yeah.
Can you go over how using the same randomness help you use the claim to just do all the way down?
Right, so the idea is instead of having to run a different sum check protocol with independent randomness for each of these 2 claims, what you can do is use the same randomness for both claims simultaneously. And it turns out that the gates you have to check at the very bottom at the end of the sum check protocol will be based on the randomness that was used from the verifier's point of view. So as long as the same randomness used in both of these things, then you'll have to reduce it the same to like final checks at the very bottom of the sum check. Yeah. Okay. Cool. And maybe I should also just tell you. Yeah, I also wanted to write out like sort of sum check like equation just because we have it for later because it's going to be important. Use up this entire board already, which is kind of awkward. So maybe I'll put it somewhere else. Yeah. Oh, we can move it there maybe. Okay. I guess I told the cameraman we would need that for, but I'll just put it here because it shouldn't be important, I guess. Or like it would be important for us, but like we did it last time, so hopefully it won't be new. Okay. So you're checking a element of like the ice layer. You want to reduce it to 2 things in the previous layer. And so what you can do is you can take an output gate and 2 input gates. And it's going to be this giant thing. So whether or not it was add gate times I plus 1 times whether like times the sum of it. And then you need to take the logic extension. Okay. And so that's the equation. What's going to happen is you're going to essentially do a subcheck with this entire thing here as a polynomial in your subcheck. So we'll come back to this later, and we'll just leave it up.
Sorry, what is DQZ?
Yeah, it's a polynomial of degree, I'm going to say it's like the size of h, maybe in each variable, so individual degree size h minus 1. Or is this taken over to the m? And it's going to basically test the quality of z and p. So if p is in this like hypercube, then it should be 1 if and only if p is equal to z, and then the logic extension of that. Okay, so today we're going to ask some questions. Okay, so we knew how to do this. So last time, yeah, I showed how to do this as long as we had Oracle access to the add and multi gates. Okay, so the goal of the first part of today's class is to remove this Oracle access. We're going to show how to get these things. Okay, actually we already a little bit more on this board. So I guess so question 1 is how to get these logic extensions. Okay, maybe you guys can tell me. Do you have any ideas? How can we get these? So I feel like Anand is bouncing, which clearly means he has something to say.
To arithmetize the circuits to give a succinct description.
Okay, good. Okay, so maybe Anand is saying something like maybe you can compute these things yourself somehow if you can arithmetize it. And we're going to see how to do this in a sec. Another way to do it is we already know how to do GKR. Like we already know how to sort of delegate a circuit, right? So let's redelegate the add and multi gates. So we're going to redelegate add and multi. And this is indeed what they do in the original GKR paper. But we're not going to do it today. So this is another thing you could do. But today we're going to show how to compute them. Actually, this is a bit weird because we're not actually going to compute the low degree extensions of these add and multi circuits. We're actually going to compute like a different, somewhat low degree polynomial on these that share the same values on like the hypercube. So it's actually not going to be the canonical LDE. I think last time Leo had said something about like can you use a different like low degree polynomial, and the answer here is yes, and we're going to see application of that today. So okay. Okay, cool. So the idea is like, okay, so if you want to compute them, okay, so you can't compute the actual canonical low degree extension. So what can you do? Well, okay, and like the reason is basically because like to compute the add and multi gates, like the circuit is kind of too complicated for you to compute yourself. So maybe here's an idea. What if instead of computing, doing GKR in the original circuit, we do it on a much simpler circuit that computes the same functionality as the circuit as you want. Okay. So idea, replace C with a simpler to describe circuit. And I guess by simpler to describe, I just mean that add and multi should be easily computable. Okay. Okay, and so let's use the universal circuit. So universal circuit is going to be a circuit that's going to take as input the circuit that you're trying to compute, along with the input, and it's going to output, it's going to simulate the computation of your circuit C on the input x, and then compute C of x. Okay, and the claim is going to be that this universal circuit is going to have a simpler description, at least for the add and multi gates, than the original circuit. Right, because it's going to take as input like the description of the circuit, and then it's going to kind of simulate the description, but all these sort of like, the simulation is easy to describe because it's very general and very easy. Okay, so maybe let's see how this will work. So we have this universal circuit here. It's going to look like this. And it's going to take as input a description of the circuit C along with your input X. And then it's going to run. The hope is that this is going to be depth d times polylog. Maybe it should be, okay, we'll talk about the depth later. So it should be hopefully not so much bigger than the circuit C, because you're going to want to still do it efficiently. What is this description C that we're here? This is, yeah, maybe I should, okay, so. Okay, so what is the circuit C? Like, how do you want to what should the input to this be like? What it's going to take, it's basically going to be a function that would tell you, yeah, so I guess it would tell you for every single, maybe there should be an add one and a mult one. So for both add and mult, it'll tell you if at a single location in the original circuit C, if there is a gate of that form or not. So it's going to be a pretty large description. It's going to be size 2 to the s. That makes sense? Yeah.
So the circuit C is going to be a size, we're going to give a description size 2 to the s.
Yes. We'll start with that. And as Ted is alluding to, so it would not be so good for us, but we'll discuss how to do in a little bit.
So these
Yeah.
are they're literally just 2-bit strings.
Yeah. And it's just going to be really long. It's going to tell you what every gate of the circuit looks like.
Doesn't P, W1, and W2 range over kind of like the horizontal distance of the circuit and not vertical distance?
Yeah, okay. Maybe we should maybe we can have P, W1, W2 range over like all the possible gates or something. So we can change the notation a little bit. That's okay. Okay.
Sorry, last
Yeah.
question. I guess this is a very small detail, but
Yeah.
how do you handle knots in the input layer?
So what you can do, this is also actually an issue with the original GKR protocol, right? Because you only have add and mult gates. What you can do is you can have x and then also the flip of x, or the not of x, and then now you can simulate everything. Okay, so how do you, so my claim is basically that this universal circuit is going to be much simpler to describe than the original circuit C. And maybe let's just see why, it's sort of, hopefully not too in detail view, but hopefully we can kind of get an idea. So the idea is let's say this is your circuit C over here. And it's going to be a bunch of layers with a bunch of gates in each of the layers, and they're going to each have some functionality. Okay. And so what the universal circuit is basically going to do is it's going to say, I want to compute this value of the circuit C gate here. Let me look at all the previous ones, because you don't know which one this is attached to. So you're going to look at all the possible values, and you're going to sort of then see what the circuit C said, and then compute the appropriate function of the previous layer based on what the circuit C says. So in particular, so in particular, in the ice layer, so the value of the circuit of this thing in the ice layer is going to be, so maybe this is a layer, and this is a gate. And it's going to be a sum of possible gates in the previous layer of the following things. So it's going to be whether C So it's going to be whether C has an add gate corresponding to the 3 gates you're picking. So this is J, and then maybe K and K prime. And then times the sum of them. So it's it's a similar thing as in the GKR thing. We're going to have sort of an add and a mult condition. And so, okay, so if it's an add gate, you're going to compute the sum. And if it's a mult gate, you're going to compute the mult. Is that okay?
Wait, what is said inside the parentheses on the add gate?
Yeah, okay, so this is going to be whether the circuit is an add gate at this particular 3 gates, J, K, and K prime. And this is going to be the values V I plus 1K, so what this value is. Yeah, sorry, so maybe this is a little bit small. Okay, I don't really know how to make this bigger. Yeah,
This is because the subscript on the C add, I actually think of it as an input to C.
yeah, exactly. So these are both going to be given from the description of the circuit C, which this will also have to take the description of the circuit C, and it's also going to read into here.
And this is the same thing that's written on the board that the
It's-
camera
yeah,
can
it's
see,
essentially the same
just
thing.
not low degree section.
Yeah.
But
Yeah.
also this is summing over OP, right? This is-
Ah, okay.
Sorry, I'm
No.
still hung up on this.
Yeah.
CAD is defined over 3 inputs, all of which range from 1 to S, right?
Sure. Okay. Yeah.
So why is it of size 2 to the? So isn't the truth table of size like S cubed?
Good. Yes. Yes. So we're going to have to deal with that in a bit. So yeah, instead of saying that the circuit C here is like the description of circuit C is too big, we're going to have to do something for that.
Wait, so why is it 2 to the S though? Because we have.
Oh, sorry, it's
three
just S.
possible-
It's just S.
Okay.
You're right. You're right. Just S.
Wait, why not F cubed?
S cubed.
Okay.
Oh, yes. That makes sense. Like, sorry, I feel like I explained the universal circuit really badly. But you're basically trying to simulate the computation of C. And to do that, you're going to introduce sort of like a new circuit, like a new small circuit for every single gate in your universal circuit that will look at the previous layer and then compute the appropriate functionality based on what C is supposed to say. Okay.
Rachel,
Yeah.
what is the P being summed over on the? Like,
Yeah.
what is
Okay.
P on the off-camera bullet?
Yeah. So these are all going to be on h to the m. H to the m here is going to be the size of like a layer.
Okay.
So it's going to be, so P you can think of as being in the ith layer, and then omega 1 and omega 2 are in the I plus 1th layer.
I see. Oh, and here, like, Z is just an arbitrary field element.
Yeah.
And P is like, okay.
So that summation there really represents like you're trying to compute that summation with a bunch of gates.
Yeah. So this is going to correspond to, I'm sorry, this is really bad. This could correspond to like a sort of a pretty big circuit here. That's going to look at the previous layer and
So the depth of U is going to be like the depth of that mini circuit times D.
exactly. Yeah, that's perfect. So
It's just looking over this part. It's local IJK metric.
Oh, that's why not.
yeah, so as I don't know what your name is, Gabe. As Gabe said, the depth of this circuit is going to be the depth of the original circuit of C times sort of like this like depth here. So the question is like, what is the depth here? Thoughts? Like roughly, I don't know. Doesn't have to be very exact. Yeah, okay, something times log s, like polylog maybe at worst. Yeah, and like the reason is because you can sort of think of this big sum as like a binary tree of sums. And then at the very bottom of this binary tree, you have like poly s many things you're kind of looking at. So this entire depth, because it's like a binary tree, is only going to be like depth like log s or something.
What's U?
The depth of the universal circuit.
Oh, like that U.
Yeah. Okay. And then what about the size of this universal circuit?
U times poly S.
Yeah, so it's going to be the size of the original circuit times like poly s. So it's just going to be poly s. And the reason for that is because the size of this universal circuit is basically going to be, for every gate of the original circuit, you have this like poly s size like circuits kind of replacing it. So you get this like poly s size here, and then times the size of the total circuit, which is poly s. Okay, so this is going to be like part of the circuit we're going to end up using to delegate instead of using the original circuit C. I guess the last claim that I made is that this circuit U is much simpler to describe than the circuit C. So in particular, the add and mode gates are easily computable or like describable very simply. And maybe let's look at this and think about it for a minute. So I guess like if you're trying to figure out, I have sort of like, I'm trying to look at a specific gate and I want to see if it's like an add or mode gate. What you kind of do is you kind of figure out where in this tree you are, right? And you can be like, oh, look, I'm part of this binary tree. It should be an add gate, right? And you're like, oh, okay, I'm an add gate. Or you can sort of read maybe in the leaves, like you're like, oh, this a particular gate corresponds to, like some add gate in the original circuit and sometimes some values, and you kind of figure out, oh, this is supposed to be a multiplicate or add gate or something. The point is that this is like a pretty easy function to describe. In particular, so there's going to be low-depth Boolean formulas that compute both the add and multi gates. So there's going to be a Boolean formula of, let's see, so it's going to be, so it's like a Boolean formula of size polylog s, that computes the add and multi functionalities. So it tells you that whether within U, these these are small formulas that tell you whether a particular gate in U is an add or multi gate. That good? Okay. Cool. Okay. And so now, like, these formulas are much easier to compute than the previous add and multi. So ostensibly, the verifier can do it themselves now. Okay, so yeah. Okay. So I guess originally, so how do you compute add and multi? We're gonna, I didn't write it yet, but you're gonna assume that C is a log space uniform circuit, which means that you can you do maybe up to time poly S computation to compute it, which is too much. Here, since the formula is only of size polylog, you can kind of just compute it yourself, right? So then when you're doing GKR and the universal circuit, you just have to do this small computation as opposed to the big one. Yeah.
And are these phi add and phi multi also log space uniform?
I guess it'd be log space uniform.
Oh.
Right? That's how it works. I mean, they're size polylog, right? So basically, what I mean by this is you can feed in any p omega 1 and omega 2, and then compute a formula of this size, and it'll tell you what the answer is. Right, so it's only polylog size, so you only have to.
Is there exists a formula such that for all p1, omega 1, omega 2,
yeah,
the formula computes it correctly?
Yeah.
Right, but yeah, I mean, the naive way I would do it is advice of polylog size, but I'm assuming there's a way to make it to get rid of this advice, right? You can make it uniform, probably.
Yeah.
Yeah.
I think it's log uniform.
I think it's just maximally. If figure out what level I is, figure out what where J is.
I think it's the universal circuit.
Yeah.
Describe. Yeah, that is.
Oh, the phi is for the universal circuit.
Yeah.
Okay. I understand.
Yeah, maybe just to summarize what we've done, we've essentially replaced this C, which has a sort of complicated add and multi gate description, with a universal circuit which has a much simpler add and multi gate description. And then now what we're going to do is we're going to run GKR on the universal circuit instead of the original circuit C. The output is still the same because the universal circuit will simulate C and compute C of X. But now the verifier can themselves compute add and multi.
The input n has increased because you have the right description.
Good. Yeah, okay, so now we're going to run a GKR on U. Maybe call U of C because it's on the circuit of, it's just U instead of C. Okay, so issues. Okay, maybe I should also write So issues, so one is that what Anand pointed out, which is that the input is now really large. So, issue one, input is large. Okay, And if you remember from the GKR protocol, the verifier at the very end has to compute some points in the low degree extension of the input, right? Before we said, okay, the input is only size n, so they can compute it by themselves. It's only n times polylog time to compute it. But now the input also has c, which is size s. So now you have to actually spend like time poly s to compute the final layer, which is bad, right? Like we wanted the verifier to be efficient. Now we're kind of back to square one. Okay, so we're gonna deal with this. Any other issues?
Sorry, in the GKR protocol, the n times poly, I guess, is, do I only need to compute a couple of bits in the input layer, or do I need to compute the entire input layer?
You need to read it all, because what you're going to do is you're going to look at the input layer and then compute something in low degree extension. And the only way you can do something in low degree extension if you know everything sort of like in the encoding. Otherwise, yeah. Yeah.
Sorry, I just have a question.
Yeah.
Before even issues, is it obvious the verifier can compute like add and multi-tilde? Given that you can compute phi add, what like?
Good.
Oh, is that the issue?
Yeah. So. Yeah, so Nikon's question is, how do you compute like the low degree extensions of add and mult? Right now, I've only given you a Boolean formula to compute them, right? So you can compute the values on the hypercube, but you can't necessarily compute the low degree extensions of them. So we're going to see how to fix those things. And hopefully, if I'm not mistaken, these are the only two issues, so we'll see. Okay. Is this okay so far? Okay, so issue 1, the input is now all of the circuit plus the original input, so it's very large. So right now, this is what our circuit looks like, is U, big part is C, and like a small part is X. Okay, so here's when the log space uniformity of C is going to come in. So if you ever read like GKR statements, the theorem only holds for when C is log space uniform, which means that there's some small description of it. So some small log S size description of C. And maybe let's call this description this. And there exists a Turing machine M that basically, if it reads in this description, it can then output like the entire circuit C. And this Turing machine should run in log space, but it can run for as much as S time. Okay. So C is too big. Yeah.
So M is like fixed.
Yeah, M is like it's a fixed Turing machine. Yeah. Yeah.
Oh, just to make sure intuitively why this matters, it's because like C has to have like somehow nice structure for it to like be defined on inputs of different lengths instead of being non-uniform.
Oh. I think one main thing is that the verifier needs to be able to like know what C is, right? Because like in order to get it sort of any hold on the circuit C for the verifier, they need to kind of have some way of like describing the circuit in some sense. This is like basically saying the circuit has to be like log size so that the verifier can hold it and like have some way of knowing what the circuit C is.
I guess I'm trying to think about like what kinds of circuits are excluded by this, like
Sure.
circuits that basically you have to write out all like the entire truth table to describe. Is that what we're trying to get rid of?
So I think Ted is our local complexity theorist, so I'm gonna
This
look
doesn't
at
go out a
that.
lot. Like basically, a circuit that you care about is log space uniform.
Okay. Okay.
You can't like hard code things though. You can't like hard code a random string or something like that.
Right.
Yeah, any uniform circuit that you care about.
Okay, so C is large, and the problem was that reading this entire thing is too much. But we have a short description of C. So let's also maybe have a circuit that computes C. Maybe we'll call this M just because we have a Turing machine called M, but it's not a Turing machine, it's a circuit. And this for a circuit will take as input the description C, like with the things around it, and then it will output the entire circuit description, and that will feed into the universal circuit we just talked about. Okay, so this circuit here is our circuit C prime that we will actually be delegating on. And just to be clear, which ones are the inputs? The inputs are this description of C, and also X. Like this entire C here is now kind of wrapped into the circuit, right? Yeah.
I have a question. I put notation like M parentheses like bracket of C equals C. So what do you mean by equals C? Like there's some other description of the circuit, or are you saying the Turing machine is able to run the circuit on any?
So it will, run in log S space and maybe up to S time, and then it can output like maybe any gate of the circuit you want.
Any gate of the circuit.
Yeah, and maybe like maybe if you have an output tape that's separate from like its actual like spaces on your compute on, you can have like you can just like output the gate one by one sort of.
Oh, okay. So you say equal C means find the gate.
Sure. Yeah. It will output the description of C. So, or like description of the gates of C. So like it will output the gates.
If you're just unrolling M, isn't that like really deep?
Good. Okay. Yeah. So what's the depth of this? So okay, M can run in time up to S. So this could ostensibly be depth S, which is bad because our verified runtime depends on the depths also. Well, it turns out you can do it in depth log S. And I'm not going to tell you to do it. You're going to tell me by the end of class. So that's sort of the goal by 3 p.m. And this will also be size S. So we'll get there, but it'll be your job to convince me and not my job to convince you. Cool. Anything else? Yeah.
Wait, how do you turn this Turing machine into a circuit?
Good. Okay. You'll tell me. There'll be hints. Don't worry. So it won't be. You should like. I think you'll be able to figure it out in the class. Okay. And then the other claim is that this is like has easy add and multi gates, and you'll also tell me to do that by the end of class. So basically, the circuit's going to have all the nice properties you want. It's going to be depth log S, size S. The whole circuit now, C prime, is going to be size poly S, because U is also size poly S. It should probably be poly S, not just size S. Yeah, and the total depth is going to be like poly log S. So yeah.
Is the statement is like truth table of M on C equals C on bracket C equals C. So do we need like size of C different copies of M, one for each
Sure.
of bits, and then
Sure.
colorize all of them? Okay.
Sure, yeah. Or you can think maybe it's a thing in like you can have like an output tape, right, where you can just like output everything to, or is that not a thing?
Yeah. I want to make sure that doesn't break.
Yeah.
No, it doesn't break logic uniformity either. You can think of a small tab like that.
Right, you might have just said this actually, but okay, so on the line there it says log S size description of C, like C in brackets. Like C in brackets is a string, it's not actually like log S, right? It's like S or something, isn't it? Or
No, this is gonna be log S size. So the circuit C is size S, but there's like a short description, like sort of tell you what the circuit C is gonna look like.
I guess if you had a family of circuits like C1 through Cn, the description could be like the number n that you should print or something. Or like a concrete example.
Sure. Yeah.
Then why is that tree there like depth log S, like wouldn't the number of leaves be S? Tree.
So this description is size log S, so the entire thing here is log S size.
It's not like a full as wide as you can tree.
I guess it kind of goes like this
Yeah,
more than
I
like, yeah, it stands out.
Oh, so for each row. Well, it depends how we
Yeah,
roll
because
it.
it's depth log S and the input side log S, so it's like roughly linear space.
There's no circuit that ever wants to go past it.
Our condition is that it's in linear space, basically. Like, I think that is actually the
But we don't know how to enroll it yet. When we enroll it, we might like, okay.
Okay, so the claim is given the circuit and giving all these properties you're going to prove to me later about, then you can do GKR. And okay, so according to our, let's see, really behind, I should push it forward here. Okay, the prover is going to run in time poly S, where S is the size of this like new circuit C prime. This is size poly S, this is size poly S, so that everything is poly S, and poly of poly is poly, so it's poly S for the prover. And the verifier is sort of the depth of the circuit plus like the input length. Depths here, this is going to be like, I think we said it was like basically depth of the original circuit times log. And this is going to be really small, it's going to be like log S. So it's going to be overall like the same depth as the original circuit. And then the input size is now log S plus n, so it's not so much bigger either. Okay, input, so okay, whatever, okay. Okay, so the second issue, and Nikon pointed out, how do you compute these, like the low degree extensions of the add-in mode gates, whereas we only currently have Boolean formulas that compute them on the, I guess in this case it's even a Boolean hypercube, it's not even like the H hypercube yet. Yeah.
Wait, I have another
Yeah.
this is fantastic, but like, okay, so the idea here was like you wanted to ultimately get like the bottom layer to be size that's small.
Yeah.
But like still like this middle layer that you get to that has like C or no net, like when you run the evaluation net, like that's big.
Mhm.
So at some point you have to be able to like get like low degree evaluations in this middle layer. Like
The prover would do it, so
the prover
you would never have to do it.
I see. Okay, I guess I'm just confused because of the GKR, the protocol we did last time was like only for circuits where like the low degree extensions get smaller, right?
They can get
but it
bigger.
doesn't matter. Okay.
It doesn't
Okay,
matter.
okay.
Because what I did is she extended every layer to size S anyway. So even if it wasn't S originally, she extended it to be big.
Okay.
So I think sometimes S can be viewed as like sort of a upper bound of like each layer size also. Okay. So second issue, how do we compute add-in mode? So we have, let me just write down what I put there, I can push this up. So we have these two Boolean formulas. And it's going to compute add-in mode. This doesn't have a square on top because it's not a linear extension. Okay, so this is what phi of add looks like. It's a Boolean formula, so it's like big tree. Not big actually, it's a very small tree. It's like polylog size. And now output at the end. Yeah, what you're like. Yeah, out of B1 up to something. So here's the inputs are all bits. So it's going to be 0, 1 to the. I guess this should be taking as inputs the size of the circuit and telling you whether or not that particular game is an add or mode gate. So this should be like size of like log n of the size of the C prime. So this should be. Okay. Cool. And our goal is to compute and so here we have H is going to be an H. And so here M is like log base H of S prime. This is what we want, and this is what we have. I want you to just repeat again, this is not the low degree extension, this is going to be a low degree extension. So what do we do for sharp set or sharp P? You guys remember? Yeah.
Sorry, I have a question.
Yeah.
It is a low degree extension, but aren't low degree extensions unique?
Oh, okay. So it's a extension that has low degree, but it's not that low. It's like somewhat low, maybe low total degree.
So we're talking about like just extension, and not necessarily
Yeah,
the lowest.
and it's not going to be the lowest degree, but it will have like low enough degree. Yeah, maybe call it low enough.
to be a
Okay.
problem.
Yeah. Low enough degree extension.
Low H.
Okay. So we can call this like the LEI. Okay. Is that okay? So it's not going to be the low degree extension, but it will be like kind of. It'll be okay. Okay. So what did we do for sharp P the first class? This is like going like 3 weeks ago. The idea there, we took like a Boolean formula or like a formula, right? Okay, let me maybe jog your memory. So the idea was you want to count the number of satisfying equations to some sort of like CSP. You first turn this into some Boolean formula, right? And then you do something to it, and then you can apply the subcheck protocol. So what do you do in the middle? Arithmetize. Like let's arithmetize this thing. Okay, so maybe first, before we arithmetize, we should change the input formats. So over here we have H, here we have Boolean, like 0, 1. But what you can do is you can just take like maybe a chunk of size like this is a really like minor detail. I think whatever. Okay, anyway, it's fine. Let's do it anyway. So this is going to be size log of size of H, and then so this is how many bits are going to be here, and you're going to take H, and you can convert it via some like polynomial. It's going to be a degree H minus 1 poly. It's going to convert any element H of your your bigger set, capital H, to a 0, 1 string. And they can do this like a bunch of times. Okay, so now we have like this like weird thing where you're feeding in H, and then you get you use a degree like H polynomial to convert it to like 0, 1s, and then now you can feed it up through this Boolean formula. And for this part, we're going to just arithmetize it. So what is arithmetizing? Just to recall, so arithmetizing is you can take like an AND gate and replace it with the polynomial a plus b minus a times b. And then, sorry, this should be and, not add. And then OR of AB is just, is this right? No, that's the other way, right? This is a plus b minus ab, and this is a times b. Right? So every time there's an OR gate here, you can replace it by this polynomial, and every time there's an AND gate, you can replace it by this polynomial. Okay, so maybe there's another lemma that Yael proved during the first class that maybe it's been too long to remember, but maybe you can try to rethink about it. So the question is what is the degree of the final polynomial you get here when you've arithmetized it?
Is it like 2 to the death?
Yeah, exactly. So it's a number of sort of input gates here. I think that's the way she said it in the first class. It's just a number of input gates times, I guess here you have to times by the degree of each sort of thing you're feeding in, which is going to be h minus 1. So it's going to be log s prime, which is the number of gates in the bottom, times, let's just say h instead of h minus 1 because it's a little shorter. Okay, so this is going to be the polynomial that we're going to use for add tilde and mod tilde. So it's not the low degree extension, but it's the thing. Yeah.
This is over F2, just to be clear. Like this extension is over, is that right? Or is this over a larger field?
Yeah, so I guess what's happening is you're first converting your H over a larger field. Yeah, sorry. Larger field. Yeah.
The way you've drawn it, it makes it seem like you're converting H into log H bits, but don't you want to convert it to a single?
So H is big, right? H is like 2 to the log H sort of information. Or okay, maybe it's the wrong way to say information, but I guess it's so H comes from this bigger set H. So you want to convert it to 0, 1, so you can feed it into the Boolean formula, otherwise it's not type compatible.
But the Boolean formula only takes in like when you fix the Boolean formula, it has a bunch of inputs that are bits, but each bit, you call them like m bit in total. So like, how do you plug in log h bits into like an input that only has one bit?
Oh, okay, yeah. So you can convert this into like a number of bits. It's going to be log h many bits.
First log in this formula.
First log n bits.
Better bits.
Or log h bits rather.
Yeah, okay, so the conversion isn't from one h symbol to one bit. It's going to be one h symbol to many bits.
To many bits.
But many is going to be log h bits.
I thought we just wanted to find like a big arithmetic circuit such that when you evaluate it when the h's are 0 and 1, it's equivalent to the original.
Okay, yeah, sure. So if you want to keep this in 0, 1, so you can have this big set here h just be 0, 1, then this is just identity. You can just plug it straight in. I guess this conversion is sort of like a, I don't know, Yayo calls the thing based on whether h is like a bigger set, so I've just been converting it to h just to match that, basically.
Oh, okay. H is different than f. Okay,
Yeah, yeah.
sorry, I got you. Okay.
You're literally just saying arithmetize, right?
I'm literally just saying arithmetize.
Okay.
Yeah. If you, yeah.
And it's still a deterministic procedure.
Mhm.
So you'll get to like some unique point given the same start point, but it's just not the low degree.
Yeah. But it's low enough degree, which is going to be this number here. Right, because if it's really low degree, it would just be h degree, but this is a log factor bigger. But that's going to be okay for us because, I guess, the verifier, that's fine, I guess, yeah.
I'm still a little bit confused about like, so VAdd is like basically computes for one gate, right? Like that's essentially like computes like given one gate, it simulates the circuit for one particular gate, right?
No. So this formula, yeah. So the input is going to be any particular like location in your entire circuit, and it's going to compute as log depths, like this polylog size formula, to tell you what that gate should be, like whether that was an add gate or not. So the input is not like the specific gate; it's going to be like any of the gates in the entire circuit.
Well, yeah. So it's okay. So it's one formula for the entire circuit, basically.
Yeah, one formula for entire circuit.
Okay. But then why are you what like? And then so where exactly what? But like we have these h's, and that means that we have technically like I guess the same number of inputs, but like we have like blocks of inputs now, and like how exactly does that change? Because that means that we have like technically we're combining like information. It just feels weird because like it in some sense it feels like we're mixing up information because we're saying like we're assigning one thing one thing in a large space to like a bunch of things in the Boolean space the field. Like we're in the large field, h is in the larger field, right? And we're saying that we're just assigning one h to this spread of things in the Boolean field, and it just feels I'm not following the logic.
Okay. Yeah, so maybe the confusion is like this part is like 0, 1, so it's really just Boolean, and then over here we have this weird h going into it, which is like not Boolean. So like what is this polynomial kind of doing with all this like Boolean stuff? So that's part of the question. Yeah, so maybe we should think about it as in like, let's first arithmetize this circuit here. So we're going to get something over a large field already. And then now we're going to plug in these like polynomials into the already arithmetized thing, which is already going to be a polynomial. So we kind of like, it's like polynomial composition.
But the thing is, you're not doing one-to-one, you're doing one-to-many.
If you think about it, the amount of information is kind of conserved, because here there's h options, capital H options for this h1, and then when you plug it up here, you now still have only h options for the resulting like 0, 1 string.
Well, I mean, yes, but it also felt that yes, but like in the higher field we only have like now we only have log s prime different inputs from the larger field. Now we're jamming them into this like, or rather we only have like a few we have much less things from the inputs from the larger field, and we're jamming that in, and it's just kind of like each element is getting is covering a bunch
just
So it turns out that there's a unique mapping from the string of h1 up to hm, and then the 0, 1 to the log s prime string. And so there's a bijection. You can go back and forth between them. So there's no like clashing. It's going to be just 1 to 1.
I'm sorry, I'm just not following the bijection. Like where does
Sure.
this
Okay. Yeah.
I guess that's like where my
Sure. Okay. So what's going to happen is maybe let me zoom out of that. It's a little messy. So let's say you have this is going to be just. So this is going to be our 0, 1 layer over here.
I'm sorry again for
Yeah. No, you're fine. No, it's good. She has questions. So this is going to be log h, number of bits. And the idea is we're going to take some h, and we're going to map it here to log h many different bits, right? So here, like one way you can do this, and you can write this in binary, right? So maybe h here is like size 8. So this would correspond to like a binary string.
Like I get you can do that, but I'm like, why are we allowed to do that, and why exactly is this helping us? Like I understand that you can write it in binary. I'm following that, but like how exactly is this helping us again? Because it feels like now each big element in the extension, like before we were just saying that like we're gonna extend each individual like we're gonna assume that like 0, 1 values are actually now extended values. But then now we're doing it in such a way that like before we were assuming these values from the large circuit are going to we're gonna say like if we have say an AND gate, then we're gonna have like plug one big value and another big value and then multiply them together.
Can I catch up really fast? How about we take a break now and then we'll come back in 5 minutes and then we'll do the second half of the class. I think that's all for this part, and then maybe we can talk offline. No, you're totally fine. Let's talk about it then. Okay. Okay, so how many of you guys know the theorem like exists or what it says or anything? Okay, it's fine. I'm going to talk about it again. So this is a really famous theorem. It's a great theorem. It's very good. Yeah, so we should talk about what these things are. So can one of the local complexity theorist people tell me what IP is? It doesn't have to be the local complexity theorist. It could be any of you.
Class of statements that can be proven with an interactive protocol between polytime bounded verifier and a computationally bounded prover.
Unbounded prover. Yeah.
Unbounded prover.
You said
oh, you did. Okay.
Let's see. Good. Yeah, so IP is a class of all statements that have interactive proofs. Interactive, that's right, okay. Yeah, so, and the prover can be unbounded time, and then the verifier should run poly time, so this means the interactive proof should also be poly size, right? Otherwise the verifier can't read it. Okay, and then what is PSPACE?
Polynomial space bounded TM languages.
Great, okay. Poly space computations, yay. Okay. Okay, and so the easier direction, so like, okay, so it was shown in 1992, these two things are actually equal. So the easier direction to show is that IP is in PSPACE. The way you kind of do that is by sort of simulating all possible like transcripts, and then you can do some counting stuff. We won't go into details, but in 1992, it was shown the other direction also held. So this is by Shamir in 1992. So in fact, PSPACE is also in IP, which means that these two classes are actually equal. And to do this, he constructed like an interactive proof for any PSPACE computation, and that would give you the inclusion. Okay, so in particular, this means that any PSPACE computation has interactive proof. Okay, so going back to like the concept of delegation, which is what this class is entirely about, right? Like how do you delegate a computation to like a bigger prover while you can run very quickly. Well, this is delegation, right? Okay. Like it's basically like I want to compute some like small space computation like polyspace, and I can like ask the cloud, hey, can you run this like awesome like Shamir interactive proof for me and just tell me like prove to me that you did it correctly, and they're good, right? Okay. So what's the issue? Like why aren't we done? Like why did we do GKR at all? The reason is because here the prover runtime is 2 to the s squared, right? So like so in PSPACE, like any computation is doable in time 2 to the s, but here's this additional so this is like s to the squared. This is like basically the time to prove is much more than the time necessary to simply compute. Which is why there's all these follow-ups works and why this is actually so an interesting question today. Okay, and there's some follow-up work. I don't know the reference, and Yao didn't either, and I don't know if her memory is wrong either. So it could be wrong, it could be true. So it's a possible statement. Okay, so it's possible that there's a follow-up work that showed how to have a prover runtime of 2 to the s log s, which is like significantly better than 2 to the s squared, but it's it's still not 2 to the s, which would be kind of the best you could hope for any arbitrary PSPACE computation. So today what we're going to show is, okay, so today the theorem is going to be as follows. So assuming GKR, which is an unconditional statement, so it's not an assumption, it's just this is what we're going to use in the proof. So since we have GKR, we can get IP equals PSPACE with a time 2 to the, I should probably write poly 2 to the s, prover. Okay, so what this means is like, so for like maybe the hardest PSPACE computations, assuming that I guess the hardest things you can do is time 2 to the s, then we do have actually efficient delegation protocols for these things. And they're in fact also proof systems, so they are like information theoretically secure. And maybe I'll just mention like one open question is, what about general time t space computations? So where t is not necessarily s, can you do an interactive proof as efficient? I think this is not known. So if you want to think about some proof systems, this is a question you can think about. Let's see. Are you guys okay if I erase this? This is probably fine, right? Okay.
Here efficient is like poly t.
Yeah, poly t. Yeah, and you definitely ask more like even like stronger questions, like can you do it with like linear time overhead, like additive whatever overhead. Yeah, there's many questions. Okay, so how do we describe a PSPACE computation? Someone said that it's a space of all computations that are doable by like a Turing machine with bounded space. So let's say that we have our Turing machine M. And let's say it runs in space S. And maybe we can say on input 0, 1 to the n. Okay. And maybe the thing we want is, and maybe we can just say time, and also time t, and let's just set it to 2 to the s, just for now, is that okay? So let's say that maybe we have a Turing machine and we want to see that within time t, which is 2 to the s, that eventually it will get to the like output, like the accepting configuration, or not. So by this point, it should get to accepting configuration. Okay, so here's sort of the trick. The idea here, we're going to use GKR to prove the theorem. So we're going to have to construct some circuit to delegate, some computation with GKR with. So this Turing machine here, it runs in space S, can run time up to 2 to the S, right? So if you naively do this, it would get depth 2 to the S circuit. That's not so good. We want it really to be depth S. Okay. So maybe I write that down. So the goal is to convert to depth S that's a goal. So here's the trick. The trick is as follows. We're going to look at the transition matrix of all the possible states of the Turing tape, basically. So we're going to have a bunch of different possible states here, and a bunch of different possible states here. So how many possible states are there? Well, there is 0, 1 to the S, because that's what the state could actually say on the tape, right? But that's also where the Turing machine is right now. So maybe times the index in S to say where the Turing machine is right now. And then, it would do like one computation, move somewhere, and then it'll be like an adjacent place at a different state. And then now the new state will be like a slightly different string, and it'll be the Turing pointer will be at a different location. So here's also going to be the same states. Okay. And the point is we're going to put a 1 at a location if there's a way to get from this state here to this state here in one time step. And zeros everywhere else, yeah.
Does this state include like the internal automaton?
Yes, that's a good point. It's actually very good, yeah.
So there should only be like one in each row.
Yeah, there should be a 1, 1 in every row because the thing you're going to do after one time step should be deterministic based on your current sort of location, your state based on your Turing, so your internal state of your Turing machine as well as what you see around you. So I'm using this as just the number of states in the Turing machine. Anything else I'm forgetting within these states? There's just a bunch of information that I don't remember. Okay. So anyway, so I guess the key point here is that this matrix is actually very easy to compute, right? Because given maybe a state here and a state here, you can sort of compare in very low depths very efficiently. So this is a very uniform description of this check, or the circuit that would generate whether or not the particular corresponding matrix value is a 0 or a 1. And that'll be important for us because we want this we want a uniform circuit, I guess. That's the point, and this would make it uniform. Yeah. Yeah. Okay. So the matrix here is easy to compute, is my claim. The reason is you can take any state here, You can do some checks. It's a small formula. You can kind of just check it very easily by knowing what M is, by knowing what you kind of see. And you can tell if there's a transition from that to the next state. So the matrix here is easy to compute, is my claim. Yeah. Okay. So maybe let's call this matrix A. So what I just said is that A, I, J, this is going to be the ith row in the j's column entry of A. This is going to be 1 if the state I goes to state J in one time step. So okay, and so that's good, right? What we really want to know is whether I will go to J or the starting configuration will go to the accepting configuration in T time steps. That's what we want. Okay, so here we have a copy of A. So we want to find what so we want to let's just do some computations just for fun and see what happens. So you have a copy of matrix A here, copy of matrix A here. Let's multiply them via matrix multiplication. So we have A squared. What is the value of the entry in the ith row and the jth column of A squared? Yeah, so I guess right here actually. So A squared, the ijth entry of A squared is whether I goes to j in 2 steps. And maybe for those of you who haven't seen this before, let's just do it so you see why. So if you want to look at the ijth entry of this product of these two matrices, what you want to do is you want to take the ith row, look at all the entries across it, take the jth column, look at all the entries down it, and you want to take like sort of the pairwise, like you want to take the product and the sum. So you want to take like this entry times this entry times this entry, and so on. So what's essentially happening is here you want to take like, you want to look at the entry corresponding to going from I to k, and then you go from k to l, k to j. And then you do this for k equals 2 also. You do it for like, can you go from I to k, and then you'll do it from k to j. And so the final entry will, the sum of all of this, these products, will be 1 if and only if there is a way to go from I to some k to j in 2 time steps. Okay, or I don't know if, okay. Okay, so in general then, if we want to look at the transition matrix of having, after going for t time steps, you can't keep doing this, right? And you get that the ijth entry of a to the tth power is whether I goes to j. Yeah.
So here, will a to the t power give you like whether I goes to j in exactly t step, like no more, no less? Oh.
Yeah, okay, that's a good point. So maybe we can say this should be in exactly t time steps, and maybe you can have your Turing machine like kind of stay as accepting configuration if it's already reached it, maybe, for instance. That's one thing you could do. Another way you could do it is you could change this matrix so there's a 1 along the diagonal so that you can always like kind of waste time if you want.
Okay.
But whatever version you want is fine. Just, yeah, maybe let's say for now, after exactly t time steps, I should reach the accepting configuration and just have it stall at the accepting place. Okay. Yeah, okay, so the point is if we can compute what AT of the input configuration, comma, the accepting configuration is, we'll know if this PSPACE commutation is accepting or not. Okay? So what we want is okay, so we're going to write a circuit to compute this. Is it okay if I'm very like loose about this? I just feel like all these things about like exactly how everything chains up is just terrible. Like it's, I don't know. Okay, so I guess like one thing you could do is you could just compute a and then a squared and a cubed and a to the 4th. This is not so good, right? Because you're going to do it for t times. Your circuit speed depth t. Okay, so what should we do instead? Yeah. Repeated squaring. Great. Okay. Yay. Okay, so the idea is we can compute this matrix A. So this is going to be like very easy to compute because we talked a little bit about how every like entry of this matrix is like you can compute it very easily, kind of just by looking at what the 2 configurations are that you're interested in. And then you can compute a squared from this by just like, I guess you do multiplication. And then you can do a to the 4th, a to the 8th, and so on. Eventually we'll get to a to the t, which I don't have room for. So this is going to be our matrix, or our circuit. Okay, let's look at the depths What's the depth of the circuit? Order. Okay, so it's like log t-ish.
Wait, but each like thing.
Yeah, okay, times something.
But like, don't you have to do? It's like you have to add up t thing to that thing, but you can make it a binary tree.
So that will have depth log. Yeah.
Okay, that's what I was. Sure. Poly-S.
Yeah, maybe you can just say poly s. It's probably like log t times like poly s anyway. Okay, so that's pretty good. Means that it's a verifier when running this computation with the prover in GKR. If it scales to the depths, its depth is now only poly s, right? What's the size of the circuit?
Just writing up.
Oh yes.
Yeah, so I guess the matrix itself is going to be size 2 to the s, right? Or something times 2 to the s. Yeah, 2 to the s, so wholly 2 to the s.
Okay, that is
2 to the s times 2 to the s is 2 to the 2s, so yeah. Yeah, okay. Okay, so if we apply GKR to this, what do we get? So let's run GKR. Oh, and actually, also at the very top, you need to then like look at the input state and then check the corresponding entry. So you want to read like this particular entry maybe, but you can sort of read it by doing some sort of like pretty small like computation on what the input and accepting conversions are. Okay, so let's run GKR. Okay, so prover runtime. Yay, okay, poly 2 to the s. Verify runtime. Yay, okay. I guess that's what we wanted to prove, huh? Okay. Nice. Okay, good work. Are there any questions about this, or does this like, does it make sense? Yeah.
Sorry, I might have missed an important point, but like, where is the cost of like actually doing the squaring? Yeah.
I guess sort of like the depth of the circuit is sort of like each square you do is going to take some more depth to your circuit.
Yeah.
Is that what you're saying?
Yeah, that's the question.
Oh, maybe I didn't understand the question.
Oh, as in like, what is the cost of squaring A? Like just going from A to A squared, what's the cost?
Sure, yeah. So how do you compute a square? You can kind of do every row and every column, and then like multiply and add them. So.
Oh, as in like you're just doing like.
You're just doing matrix multiplication.
I see.
So maybe you can tell me how long this takes.
Or definitely SU.
Oh yeah.
So it'll be gone.
But are we supposed to know how that thing that you said we need to prove to you? Are we supposed to know?
Oh yeah, that's a great question. Oh yeah, so okay, earlier, okay, I already erased it, I think. Wait, are there any more questions about this before we go back to that?
We're not going to use this to prove that because I know we think.
You can't use IP PSPACE to prove it. Or you're allowed to use the logic we just had.
Okay.
Yeah, so how do we construct the circuit now?
Oh, so that's another reason we need to log space uniformity.
It runs a log space, so it's a Turing machine, so that's great.
Yeah.
Yeah, okay. So this is basically a scaled down version of that, right? This is log space uniform, so you're running in log space. There you're running in times like space s, so this is a exponentially smaller version of that. So all the parameters over there, you scale them down. So we have the depth over here was poly s. The log of that is like log s, right? The log of the size here is s. So we have all those things we wanted.
How do you incorporate the input into this Like you need to know what the starting state is.
With this one or with IP PSPACE?
With that one.
The input state, yeah. Yeah, so I think the way I normally think, or I like to think about it is you only check the input configuration at the very end once you complete the entire thing. So then you only have to read like the input comma accepting configurations entry. And there you can just kind of like do like a formula to like sort of read off what it says and then look at the corresponding value.
That's great. So like almost the entire circuit is just like doesn't even read the input.
Yeah, it's only the very end.
But I mean, this is for accepting, and that one doesn't really accept it prints.
Yeah. Yeah. Okay. So maybe. Yeah. So I guess like each configuration corresponds to like it's a configuration, right? So there's like some like data about like what the gate's output, like gate's value is or something. And maybe you could read off the value there.
Like each entry is like input comma is the gate here or not, and then each entry.
Sure.
And this is like an easy add fault situation, right? 'Cause it's
Yeah.
just multiplication.
Yeah, the important point here is that computing the matrix A is very easy. That's really the key thing here. And that's also why when we said what, we were put it behind, but when we said what A looks like, it really had to be like also where the Turing like pointer was, right? Because if you didn't know where the pointer was, it could be very large, yeah.
But the
Sure. So, wait, you can like factor out what you're saying into the form of like if you have a low space computation, you can turn it into a low density circuit. Is that a fair model
Yeah.
that you've used?
Mm-hmm. Yeah, it's actually a kind of interesting statement, huh? I don't know. I didn't know that you could do this until recently either. So I guess like the interesting thing here is instead of being like a really tall and skinny computation, you can turn it into a circuit that's really fat and like kind of short.
That's why we're getting quadratic depth, not
Like,
Wait, sorry, okay, just in terms of like where we're at in class. So we just proved this theorem. And is this like the same reasoning for why the log space uniformity thing works out too? Why this thing works?
You tell me.
Sarah, you tell me. I'm delegating the
It's kind of weird because you don't actually take A as input. A is like kind of like hard coded into the circuit, right? Like that's why like the input can still be like the small thing that's just describing the starting state.
Yeah, like the Turing machine M is sort of what determines what the circuit actually looks like. So maybe as part of the input of this, you're also going to have a description like the Turing machine in its entirety. The Turing machines are like finite size, so it doesn't matter.
Yeah. And then you can
And that's why we don't need to worry about complicated add multiple predicates inside M, because it actually just looks like this.
Mm-hmm.
Yeah, I'm still kind of weirded out by the fact that like all of that until the star at the top, all of this is like not even dependent on the input. So it's like in this case it's just going to be constants like zeros and ones. So then like why are we going through the trouble of like computing all these layers instead of just like using the top layer where we like?
Oh yeah, I mean, how do you hold the top layer?
So you're saying that like it's easier to encode the entire computation thing than just the result.
It's easy to say what you have to do to compute it than to actually compute it.
C has very little complexity. This is just like the present C.
Or in this case it's M, not C.
M computes C.
Or like bracket C is a compressed representation of C. M is the decompressor, and C is the.
But I'm saying like why don't you just hard code in the top layer of M?
That would have description size of roughly C.
It doesn't even use or
Well, it's just it's just a string of like size of C. So you can't hard code that, it's less efficient.
okay, it's weird, but I can kind of feel it.
So
this trouble, and we're able to go through this trouble because we assume that C can be described succinctly, like log space succinctly.
Yeah.
Is polylog S uniformity enough? That's make everything work?
I'm gonna delegate like question to somebody else. I don't know how like log blows up. Probably not, right? Because if you take like the transition matrix A you have is going to be 2 to the description size or whatever, like the space, right? So if you have like larger space, it's really bad.
But like space S gets turned into depth like S squared roughly in this transformation.
Yeah.
And so if we have like space S squared to start, we get depth S to 4, this is okay.
Yeah, but then the question is the prover runtime, right? But the reason why we're doing any of this is because of prover runtime. You actually get an advantage in the prover runtime. Anyway, so we're done early, so maybe we can all go get some corn. And, yeah.